All right, we're starting off on a new chapter now, dealing with what we call stoichiometry. Stoichiometry is a process in which we can predict what our amount of products are going to be, depending upon how many reactants, or what type of reactants, or how much the reactants we have. The stoichiometry deals with the coefficients in a balanced equation. In other words, when we did balanced equations, the numbers in front we called coefficients. Now, let's take a look at what is going on with that. So let's take the synthesis of water. And the balanced equation for this is 2 hydrogen gases reacts with 1 oxygen gas to produce 2 waters. Now, the numbers 2, 1, and 2 is coefficients, even though we don't have a 1 there. It's assumed that to be 1, and correctly so. But what do those numbers represent? I said, just now, 2 of this, and 1 of that, and 2 of that. 2 of what? Of the hydrogen. 2 of 1 of what? Of the oxygen. 2 of what? Of the water. If you said molecules, you'd be correct. This is basically saying 2 molecules of hydrogen added to 1 molecule of oxygen will produce 2 molecules of water. And so if we want to predict how many molecules we're going to get, this is great. But most of the time, we can't see what a molecule looks like. We could if we have the right type of equipment, but we're at high school, we're not going to have that. But what we can do is predict the amount of mass, or the number of moles, or whatever. But we start with this. Now, we're gonna change this relationship to moles, and this is how we do it. Now, if you remember, the definition of a mole is what? What number is associated with 1 mole? If you said 6.02 times 10 to the 23rd, you would be correct. There are 6.02 times 10 to the 23rd molecules in 1 mole. So if I multiply this by 6.02 times 10 to the 23rd, and each part of these this section here, we're going to do that. We're going to multiply each by 6.02 times 10 to the 23rd, and multiply this by 6.02 times 10 to the 23rd. Now the question is, why are we doing this? Well, this is actually a ratio of 2 to 1 to 2. This ratio is the relationship of the number of molecules in this reaction. And since we're saying that these are molecules, the label for each of these then is going to be molecules. And I'm using MLC for abbreviation for molecule. I figure if mole can have a 3-letter abbreviation, MOL, then why not use MLC for molecules? So anyway, and I'm going to multiply each of these by this number right here. And this gives me a new ratio. This is 1.204 times 10 to the 24th, 6.02 times 10 to the 23rd molecules, to 1.204 times 10 to the 24th molecules. And as we know, if we multiply every part of a ratio by the same number, the same ratio exists. So these 2 ratios here are exactly the same, just written differently. So when I take a look at this, it's a pretty ugly looking ratio. But what I'm going to do now is I'm going to multiply it by something else. I'm going to multiply it by the definition of a mole. And like we just said, a mole is 6.02 times 10 to the 23rd of anything, in this case, molecules. So I'm going to multiply each term of this ratio by 1 mole over 6.02 times 10 to the 23rd molecules. 1 mole over 6.02 times 10 to the 23rd molecules. Anybody remember what we call this number besides mole? There's another name for it. Anybody know? 1 mole over 6.02 times 10 to the 23rd molecules. If you said Avogadro's number, you would be correct. Avogadro's the guy who came up with that. They named it after him, Avogadro's number. He called it mole. They called it Avogadro's number. Well, when you multiply these out, molecules cancel out here, here, and here, leaving moles in each case. And when you divide that out, you get 1 mole of hydrogen for every, I'm sorry, that's 2 moles of hydrogen, my bad. 2 moles of hydrogen here for every 1 mole of oxygen here for every 2 moles of water here. Okay? Now, what was the point of that? Well, the point of that is explaining to you that when you see a chemical equation like this, it refers to molecules and moles. Not at the same time, you refer to all molecules or all moles. We're going to take a look at the moles on this. Okay? So, let's go back to that equation. 2 hydrogen gases plus 1, and let's put mole there. It is mole, but we're not writing it up there. 1 oxygen, and I should not put the 1 up there, so let me get rid of the 1. Plus 1 mole of oxygen yields 2 moles, and I'm writing moles again, thinking ahead of myself, 2 waters. And again, I'm thinking in terms of moles and not molecules now. So let's suppose that I have 43.5 moles of hydrogen. And I want to know how many moles of water am I going to get out of that? Well, if you looked at the ratio, you can probably figure it out. But we're going to show the mathematical conversion for this. So this is a conversion problem, much like we learned way back when in the first couple of chapters. So we write down 43.5 moles of H2 times fraction line. And we're going to convert moles of hydrogen to moles of oxygen. Okay? Now, we can get those numbers from this because, as we said, this is both molecules and moles depending upon the context. Where our context here is moles. So that means that I just go find hydrogen and see the number in front, which is 2. Oh, I'm going to go to water, not oxygen, so let me change that right there. This is H2 right here. I'm trying to get that right there, okay? And then I go over here, and I got 2 moles of water for that. So on my calculator, I'll take 43.5 times 2 divided by 2, and not surprisingly, my answer is going to be 43.5 moles of water. Okay? So let's take another scenario. Let's suppose that I have 43.5 moles of oxygen. And I want to know how many moles of water I'm going to get out of this. Okay? So again, this is a conversion problem. 43.5 moles of oxygen times fraction line. And I'm going to put this in the denominator to cancel it out. And I'm going to put moles of water on top. Okay, so moles of water, as we said, is right there is that 2, and moles of oxygen, there's nothing in front, so that's a 1. So that's going to be 2 on top, 1 on the bottom. So my answer for this is going to be 87.0 moles of water. That's how mole-to-mole conversion works. Okay? So let's do another problem. Let's take another equation and let's use the synthesis of ammonia. N2 gas plus 3H2 gas yields 2 NH3 gas. Okay? Now let's suppose that I have 0.688 moles of ammonia. Or let's just say I want 0.688 moles of ammonia, and I need to know how many moles of nitrogen, or let's say hydrogen, how many moles of hydrogen I'm going to need in order to create that. Okay, so we need to be able to have the right amount of hydrogen to make this stuff work. So I got 0.688 moles of ammonia times fraction, and again, I've got to get rid of the moles of ammonia, so that goes in the bottom here. And on top goes moles of hydrogen. Okay, so we go to the hydrogen here has a 3, so put a 3 on top. We go to the ammonia, and that has a 2 in front. And we see here the moles of ammonia cancel out to leave us moles of hydrogen, which is what I want. And when I multiply this out, I take 0.688 times 3 divided by 2. The answer is 1.03 moles of hydrogen. Make sure that's right. Oh, I'll read that's right. 344 times 3 is 12, 13. Oh yeah, it is right. All right. So that's how you do conversions. And then the next one, we're going to get into a two-step problem. And there'll be other stoichiometry problems with even more steps. So, practice problems are at the end of the script here. This time we're using this equation right here. 2 benzenes plus 13 oxygens yields 12 carbon dioxides and 6 waters. So I want you to do those conversions. Remember, do the conversion underneath the problem, then fill in the blank with your correct answer. Have fun.